Good morning, everybody, and welcome to Homework Helper for section 8.1. Let's go ahead and go into the first section here with the ready, which is reading function values in a piecewise defined graph. Now, when we're talking about piecewise, what we mean is that some of these graphs will behave differently on different parts of our domain. The number 1 and 2 are just going to be some standard quadratics, in which case we just have to find the value that corresponds with the value given. So here we're told f of -3, so all we have to do is find where x is -3 and find our y value. So a quick little zoom in, 1, 2, 3, we see that it's there, we see that it's 0, etc., etc. But what I really want to look at are these other ones, 3 and 4. So let's go down to those real fast. Let's look at number 3 here. And what we'll see is that this line is going to behave slightly differently. It's going to behave like a straight line here, like a different straight line here, and then like a third straight line along that third edge there. So we have to be looking at all of this. So when we see h of -4, 1, 2, 3, 4, we see that it's, whoops, 1, 2, 3, 4. There we go. It's right there. We see that it's at -1. H of 0, so when x is 0, we see that y is 3. H of 2, it's right here. We see that it remains 3. But when we go over one more to 4, we see that we go up to another 4. So just following the different ways that the line behaves, whether it's going up flat or up at a different rate. Or even when we look at number 4 here, we see that it kind of has that partial parabolic shape as we go from here to here, from -2 to 1, it behaves like a parabola instead of a straight line. So just be mindful of that and how they're all behaving. Okay, let's go ahead and continue on. So here we're going to be writing piecewise functions. So let's go ahead and look at this. What we want to do is we want to see how each parts, or how all these parts behave differently. So before I even read the paragraph for number 6, I see that I'm going to have two pieces to this function. I see one piece that behaves like this, which is a flat horizontal line, and then I see that I have one piece that's behaving like this, with is a positive but still a linear behavior. So let's go ahead and read what the situation is. A parking garage charges $3 for the first 2 hours that a car is parked in the garage. After that, the hourly fee is $2 per hour. Write a piecewise function p of x for the cost of parking in a car for the garage for x hours. And so here's our graph. And so what we can do with this is we can see how each of these pieces actually behaves. The very first piecewise function asks us, it tells us that it's $3 for the first 2 hours. So we see that here for the first 2 hours, it remains flat at 3. So when we're thinking of writing this as a piecewise function, we know that as we go from 0 to 3 hours, we know that our function is going to be just p of x equals 3. But then, as we go from 3 to infinite number of hours, well, not infinite, but as long as you want to park your car, we see that we have this behavior instead. Okay? So when we're looking at this behavior, we're going to have to figure out what exactly is our slope, what is our linear equation here. So from here, from this edge, it's going to be p of x equals what? Well, this is a line. And if we were to follow it backwards, right, because we see that we're going up 2 over 1, if we were to follow it backwards, we would see that our intercept would be at -1. We see that our slope rises 2, runs 1. So our m is 2, our b is -1. So I can just write this as a slope-intercept line. P of x equals 2x's minus 1. Okay. And so now this looks kind of ugly, right? I just kind of did my doodles here. So let's write this nice and neat. So I would say that this is p of x equals, and then I would do this giant bracket thing. Okay, and I say p of x equals 3 when 0 is less than x this is less than or equal to 3. And then I would say it equals 2x minus 1 when 3 to infinity. Okay, and so now we understand the piecewise a little bit better. So this is our limit on our domain, right? This is our domain. And when our domain is between 0 and 3, I'm sorry, 0 and 2, why did I write 3? 0 and 2, let's get this right. 0 and 2 hours, we know that we're only going to end up paying $3, but the minute we go over 2 hours, we suddenly have to pay an additional rate of 2x minus 1. Okay. Next, it wants us to write equations in point-slope form. And so for this, it's going to be important to know what point-slope form is. Point-slope form is going to be y minus y1 equals m times x minus x1. So that whenever we have a slope, we can just plug in our values here so that we get, for this one, this will be y minus our y value equals our slope times x minus our slope value. And so that will be our answer. And there we go. That's going to be it. Let's just double check. Let's plug in our x. So if I plug in x here, that should get my answer. So if I plug 1 in for x, I get y minus 2 equals 3 times 1 minus 1. And if I've done this correctly, my y should be 2. So this becomes 0. This is 0. Add 2. Cool. So when I plugged 1 in for x, I got 2 for y. 1, 2. Great. I did it correctly. But again, all this is just plugging things in the right place, right? The y1, x1, that just means any real point, okay? Any point that's actually on our graph. And then the m we just plug in. For 11, 12, and 13, we get an additional wrinkle in that we're still being asked to write it in point-slope form. But this time it's mean, and it doesn't give us the slope. So that means we have to find the slope using the slope formula. Slope formula. And that's going to be our rise over run, remember? And our rise is our change in y over our change in x, or to put it even more explicitly, y2 minus y1 over x2 minus x1, where this is our second point and this is our first point. So let's go ahead and look at number 11 here, for example. I'll call this our first point, I'll call this our second point. So the y value of our second point is 5, and I'm going to subtract the y value of our first point, which is 0. I then see that the x value of our second point is negative 4, and I'm going to subtract the x value of our first point, which is 0, giving me 5/4 negative. So now that we know our slope, we have two options because we have 2 points given to us. So I'll do it for both k and l. So it's going to be y minus y1 equals m times x minus x1. So I know my slope is negative 5/4. The y value of that point is 0, so that's just going to be y equals a negative 5/4 x minus 0, so just negative 5/4 x. Now that's if I picked k. Now look at what happens when I pick l. This time it's going to be y minus the y value of my point, which is 5, and that's going to equal a negative 5/4 x minus the x value, which is a negative 4. So instead of writing minus negative 4, I'm going to write plus 4. And what I want you guys to see is that these two equations represent the same line, right? These represent the same line. They both have the slope, they both have a point. And so there's actually an infinite number of ways to write an equation in point-slope form, just as there are an infinite number of points. But these are going to be the exact same thing. And we can even prove that, which I think I will do right now. So to prove that these are the same, I'm just going to evaluate this to see if I can get it into this form. I'm going to distribute the negative 5/4. Give me y minus 5 equals a negative 5/4 x. And negative 5/4 times a positive 4 would just give me a negative 5. I'm then going to add 5 to both sides, giving me y equals negative 5/4 x. And you'll see that it's exactly the same as the other point version. So either way works. We get to choose which point we want to use, which can be challenging because there's multiple points. But what we see here is that it doesn't matter which point we choose because it is the same relationship. We have proven that. All right, that's going to be your homework for today. Good luck, everybody, and I will see you tomorrow.